Hello, everyone. Today, we are going to learn about preliminary mix proportion design of ordinary cement concrete. The calculation of preliminary mix design is primarily based on empirical formulas and consists of the following 7 steps. 1. Determine the design strength of concrete, FCU O. 2. Calculate the water binder ratio, W/B. 3. Select the unit water content, MWO. 4. Calculate the unit amount of cementitious materials, cement, etc., MCO. 5. Select the sand ratio, beta S. 6. Calculate the usage of coarse and fine aggregates, MSO, MGO. 7. Calculate the preliminary mix design. First, let's determine the concrete design strength FCU O based on the required concrete strength grade and the quality management level of the construction unit. Here, it is explained that when the design strength grade of concrete is less than C60, it can be calculated according to the formula FCU O equals FCU K plus 1.645 sigma, where FCU K refers to the design strength of concrete obtained from drawing data. Sigma represents the standard deviation of concrete strength, reflecting the production level of concrete, which can be obtained from the table above. Next, we determine the water binder ratio, W/B. When the design strength grade of concrete is less than C60, the water-cement ratio is determined according to the formula. Let's first understand the meanings of the symbols in the formula. W/B represents the water binder ratio in concrete. Alpha A and alpha B represent the regression coefficients of aggregates, which can be determined by referring to tables based on aggregate types. FB represents the compressive strength value of cementitious materials at 28 days, which can be determined through mortar strength tests or according to the formula. Additionally, the calculated water binder ratio must meet the durability requirements of concrete. This means that based on the environmental conditions, we need to determine the maximum allowable water binder ratio. The calculated water binder ratio from strength calculation should not exceed the maximum allowable value. If it does, we typically choose the maximum water binder ratio allowed for durability. For example, as shown in the table, for a certain environmental category, concrete with a strength grade of C20 should have a maximum water binder ratio of 0.60. Next, let's determine the unit water content. The unit water content for dry and plastic concrete should be determined according to the following rules. When the water binder ratio of concrete is in the range of 0.4 to 0.8, selection can be made according to the table below. Table 1 represents slump values. Selection is based on the slump values, and Table 2 represents the selection based on VB consistency values. When the water binder ratio of concrete is less than 0.4, determination can be made through testing. When determining the water content according to the table, the values usually refer to the usage for medium sand. If fine sand is used, the water content per cubic meter of concrete can be increased by 5 kilograms to 10 kilograms based on the table. And if coarse sand is used, it can be decreased by 5 kilograms to 10 kilograms based on the table. If mineral admixtures and additives are used, the water content should be adjusted accordingly. Next, let's determine the quantity of cementitious materials. The quantity of cementitious materials can be determined using the unit water content and water binder ratio. As mentioned in Formula 1, multiplying the unit water content by the water binder ratio gives the quantity of cementitious materials. The quantity of mineral admixtures in cementitious materials can be determined according to Formula 2. That is, the quantity of mineral admixtures is equal to the quantity of cementitious materials multiplied by the dosage of mineral admixtures, which is typically determined through testing. The quantity of cement in concrete is calculated according to the following Formula 3. In other words, the quantity of cement is obtained by subtracting the quantity of mineral admixtures from the quantity of cementitious materials. It should be noted that the quantity of cementitious materials calculated using the above formulas is to ensure durability. Additionally, it should meet the minimum quantity of cementitious materials required based on the environmental category of the concrete structure, as shown in the table above. Next, let's determine the sand ratio. When the slump is less than 10 millimeters, the sand ratio of concrete should be determined through testing. When the slump is between 10 millimeters and 60 millimeters, the sand ratio can be determined based on the type of coarse aggregate, maximum nominal particle size, and water binder ratio according to the table. When the slump is greater than 60 millimeters, the sand ratio should be determined through testing, or adjustments can be made based on the table by increasing the sand ratio by 1% for every increase of 20 millimeters in slump. There are a few points to note regarding the sand ratio determined from the table. Firstly, the values given in the table refer to the sand ratio for medium sand. If fine sand or coarse sand is used in the concrete, the sand ratio should be correspondingly decreased or increased. Secondly, when artificial sand is used as fine aggregate, the sand ratio should be increased appropriately. Thirdly, if only one single particle size of coarse aggregate is used, the sand ratio should be increased appropriately. The determination of the quantity of coarse and fine aggregates can be done using two methods: the mass method and the volume method. The mass method assumes the apparent density of concrete. The apparent density of concrete refers to the sum of the unit masses of each constituent material in concrete. With the unit water content and the quantity of cementitious materials already known, there are only two unknowns: the quantity of coarse aggregates and the quantity of fine aggregates. The relationship between the quantities of coarse and fine aggregates is determined by the sand ratio obtained earlier. Thus, we can establish a system of linear equations as shown in the figure above, and solve for the quantities of coarse and fine aggregates based on these equations. Another method is called the volume method, which considers the volume of concrete as 1, consisting of the volumes occupied by various constituent materials and the volume of voids in concrete, as shown in the formula above. When we know the densities of each constituent material, the ratio of mass to density allows us to obtain the volumes of each material. The sum of the volumes of each material, along with the volume of voids, constitutes the volume of concrete, which is considered as 1. The unknown here are still the quantities of coarse and fine aggregates, and their relationship can also be reflected using the sand ratio. This forms another system of linear equations, and similarly, we can solve for the quantities of coarse and fine aggregates. The mass method calculates the quantity of aggregates straightforwardly and intuitively, which is easy to obtain. On the other hand, the volume method requires prior knowledge of the density values of various materials, and this density should correspond to the materials actually used, resulting in a more accurate mixed proportion. The focus of this lesson is to understand and master the preliminary mix design of concrete. Preliminary mix design calculation involves many parameters. During the calculation process, attention to detail is required, and a thorough understanding of each symbol and value is necessary to ensure the accuracy and feasibility of the data. It is hoped that through this lesson, you can grasp the correct methods. Thank you for listening attentively to this micro lesson. Goodbye and see you again.